We're going to start with number 11. That one, first we'll write it down. X squared plus x, okay. And what they ask us to do, we're not actually graphing anything quite yet, we're just getting started. And they ask us to find, from our steps that we talked about in the intro video, the vertical asymptotes and the x-intercepts. And those are the only two things they want us to find, and before you have done it, you wonder, why would they ask me to do that? How are they related? So let's talk about that. So we're not going to graph this, but let's think back on the previous section when we did graph. What did we get? In the previous section, we got a vertical and a horizontal asymptote. So let's talk about the vertical asymptote, because that's what they want us to find. So in the previous section, we get a vertical asymptote here, or maybe at -4, somewhere. We got a vertical asymptote. And what was that vertical asymptote saying? If we got one, say here, that was saying this x value is bad. Stay away from this x value. This x value does bad things. And what makes a value, an x value, bad in a rational function? So the only thing that would make a bad choice for x, a wrong choice for x, would be one that makes the denominator 0. That's the only thing that you just can't do. You cannot divide by 0. So anything that would make the denominator 0 would tell you there should be a vertical asymptote there saying, no, this is a bad value for x. So if we took the denominator and set it equal to 0, just out of curiosity, just wondering, what values of x would make this this expression here, or the denominator, equal to 0. Right, so to find the vertical asymptote, we will set the denominator equal to 0, and then solve for x. So we can factor out an x here, get 3x plus 1 equals 0. So x equals 0, or 3x plus 1 equals 0. So that's already done. X is 0, or x equals -1/3. So at these two places, you'll find vertical asymptotes. Okay. So vertical asymptotes at x equals 0 and x equals -1/3. All right. So how is this at all similar to finding x-intercepts? An x-intercept would be wherever this function is equal to 0. Right? Wherever this is equal to 0. And we talked about this at the end of the previous section sample problems. If we multiply both sides by 3x squared plus x, to try and simplify things, we find x cubed plus 27 equals 0. Right? Because it cancels out here, and 0 times anything is 0. So all we have left is the numerator equal to 0. That makes sense, because if the numerator is 0, it won't matter what the denominator is. 0 divided by anything is going to be 0, with the exception that the denominator is also 0. Okay, that'll never happen to us, I don't think, this year at all in Algebra 2. We'll talk about it next year in pre-calc. But, so that's just not going to happen. That we'll have 0 in the numerator and denominator at the same time. So we set the numerator equal to 0 because if the numerator is 0, if we divide 0 by something, it's still 0. So then the function will be equal to 0 whenever the numerator is equal to 0. So we'll solve for x. Take the cubed root of both sides. X equals -3. Okay, so we have x-intercept at x equals -3. So we found the x-intercept, the vertical asymptotes, and that's how they're related. To find vertical asymptotes, set the denominator equal to 0. So we set equal to 0 to find the vertical asymptote, or asymptotes. You see we found 2 of them here. And then this guy, set equal to 0 to find x-intercepts. Right. So Good. Let's do that for the next one. We're going to kind of jump around here. We started with 11 because 11 had both vertical asymptotes and x-intercepts. Let's see what happens with number 7. Y equals 5 over x squared minus 1. Good. So we're going to find the vertical asymptotes and the x-intercepts. So vertical asymptotes, remember, those are the values of x that are bad, right? If we had a vertical asymptote right here, it'd be saying bad x. So that would be anything that causes the denominator to be 0. So we're going to solve here. X squared equals 1, x equals plus or minus 1. So we've got 2 vertical asymptotes, one at positive and one at negative 1. All right, and now we'll find the x-intercepts. So the function has to be equal to 0, which means the numerator has to be equal to 0. But how do we make 5 equal to 0? You can't. It's impossible. So there are no x-intercepts. Okay, so vertical asymptote there, those 2 places, and no x-intercepts. Let's do number 8. Y equals x plus 1 over x squared plus 5. So finding the vertical asymptotes, we're going to take the denominator, set it equal to 0, and solve. So x squared equals negative 5. Take the square root of both sides. X equals plus or minus the square root of negative 5, and we call that I times the square root of 5. So that's where the vertical asymptotes are, except for these are not real. They're imaginary. And we only graph real numbers on our axes like this. When we draw an x and a y, those are all real numbers, no imaginary ones. Okay, completely different graphing system for imaginary numbers, and we're not even going to worry about that this year. So no graphing of imaginary vertical asymptotes. So effectively there are no vertical asymptotes. Now let's find the x-intercepts. We'll take x plus 1, that's the numerator. Set it equal to 0. X equals negative 1, that's your x-intercept. So x-intercept at x equals negative 1. All right, so it's possible to have both x-intercepts and vertical asymptotes. It's possible to have just one of those. So something to bear in mind as we work through these. Just picking our next color here. Number 15. Y equals 2x over x squared minus 1. Okay, so we're going to do the whole thing. We are going to do all these steps. We're going to graph this function as a whole. Ready, go. All right, so first we're going to find vertical asymptotes. We've done that several times now. We're just going to take the denominator equal to 0. So step 1 will be this. X squared minus 1 equals 0. X squared equals 1. X equals plus or minus 1 when we take the square root of both sides. So we got a couple of vertical asymptotes here. Let's do step 2. Horizontal asymptotes. Actually, let's go on to step 3 because we already know how to do that. Let's do that. Horizontal asymptotes, or sorry, x-intercepts. We'll take 2x, set it equal to 0, and find x is equal to 0. So we have our x-intercepts there. All right, so here's a new thing. Horizontal asymptotes. Okay, if you go back to the previous section, if you want, a more like a discussion on the basic concept of a horizontal asymptote, it's that value that the graph approaches, gets really close to, but never quite gets there, right? If we had a vertical asymptote here, then our graph might do something like this. Okay, that's just a hypothetical. So it'll get really close to this value, but never quite get there ever. So how can we find that value for this? So think about when we say it gets close to that value, but never quite gets there, we're talking about when we put in really big values for x in the positive direction. Let's bring that back up. talking about when we put big values in for the x, in the positive direction, and big values in for x in the negative direction. So let's look at this function. That's why this is also called, the horizontal asymptote is also called describing the end behavior. Okay, the behavior of the graph at the ends, not the middle. Forget about the middle. For now, when we talk about the horizontal asymptote, we're talking about the ends, end behavior. What happens when we put a really big number in for x in the positive and a really big number in for x in the negative? What value we're going to get close to? Let's put a big value in here. We could just throw a big value in for x. Let's bring out our calculator and do just that. Clear out that. So let's put in 100. Okay, so here we go. Here's the numerator. 2 times 100. So there's our numerator, and we'll do the denominator now. 100 squared minus 1. All right. So let's think about this. Is going to be 200 over, well, 100 times 100, that's 10,000. Minus 1, 10,000 minus 1, that's 9,999. So you got 200 over 9,999. That's a pretty big difference. 200 versus 9,999. Let's hit that. So this is 0.020002. So that's pretty small. 0.0, and the first number that we get is not 0, is a 2 here. Not very big number. Let's try 1,000. So I'm just going to bring back up by hitting second enter. I bring up the last thing that I put in there. And I can change this second insert so that I don't just write over the parentheses, but I push the parentheses over. And then I'll do the same thing and make this 1,000. All right, so we have 2,000 over 1,000 times 1,000. Now that's a million. This is getting much bigger, much faster. This is just 2,000. This has gone from somewhere around 10,000 to a million. So we got 2,000, pretty much 2,000 over a million, right? Notice how it's really what you put in for x that matters. I mean, we put in 1,000 for x and we square it, and then we subtract 1. That's not a very big deal. We got a million minus 1. That's not much different from just a million. So we got 2,000 over a million. That's even smaller than before. Let's go really big now. Let's just make x a million. So we'll put in a few more zeros. And we'll go over. We'll insert 3 more zeros. So we have 2 million over, now this is a million squared. That's huge. A million squared. What would that be even? So you got 1, 2, 3. So this would be 1,000, million, billion, trillion. So that's a trillion down there in the denominator. A trillion minus 1. Big deal, minus 1. That means nothing. This is 2e negative 6. Remember, that means 2 times 10 to the negative 6. That means move the decimal place to the left 6 places. So this is 2 times, right? So we'll take 2 and we'll move it 1, 2, 3, 4, 5, 6. 1, 2, 5, 6. We put the decimal place there and we get all these zeros. That's really small. What's going to keep happening is we'll get smaller and smaller and smaller numbers as we put in bigger numbers for x. Okay. Now, that shouldn't be surprising because we have a 2x here. So we're going to take x and multiply by 2, so that's, going to make x twice as big. But down here we're taking x and we're squaring it. And just x to the first is nothing compared to x squared. X squared is really big, where x is just not that big. So we will multiply by 2, x by 2 here. We're going to multiply x by itself down here. And as we noticed, subtracting 1 is not going to make that big of a difference. So this denominator is going to be so much bigger than the numerator that what are you going to get? You're going to get something that's pretty much 0. As x gets to be very, very large, y tends to get smaller and smaller and smaller, closer and closer and closer to 0. So since it is approaching 0, getting closer and closer and closer to 0, our horizontal asymptote is at y equals 0. So let us get rid of this that is in our way. Right, and we're gonna graph this. Let's start to graph some of this. We got vertical asymptote at positive and negative 1. So here's positive 1, negative 1. We'll put vertical asymptotes there. Great. We got an x-intercept at 0. Cool. We got a horizontal asymptote at 0. Let's just make that a different color so we can see. It's going to go right over top of the x-axis. So we've really got a lot of information here. We know that we are not going to be able to cross these vertical asymptotes. Don't make the mistake of thinking you can't cross the horizontal asymptote. Never said that. You can in the middle, right? The horizontal asymptote has to do with the end behavior, not the middle. Remember I said forget about the middle. Horizontal asymptote has nothing to do with the middle. If you want to, you could just not draw it in the middle to not create any confusion. So we can't cross the vertical asymptote. We have stuff happen in the middle here. We're going to figure out what's going on in the middle. And then on the ends, we know we're just going to wind up approaching the horizontal asymptote. So how do we figure out what's going on? And here's what I mean. These are some things that could possibly be happening. All we know right now is that we can't cross these vertical asymptotes. We've got to either touch or cross this x-intercept, and at some point we have to, on the ends, approach the horizontal asymptote. So here's a possibility. Let's pretend I actually drew that through that x-intercept. Then this could be coming down like this, and this could go like that. That's a possibility. Let's try another one. This could come down like this, only touch the x-intercept and go back up. And this could go like that there. And let's say on this side it does something similar to the red. Go like that. See how just imagine all the possibilities that you could think of. How do we figure out what's going on? For one thing, we got to know, at the vertical asymptote, are we coming from way above here, way at positive infinity, or way down here? Okay, so we got to know what's going on there, close to the x, or to the vertical asymptote. Then at the x-intercept, what's going on? Are we going to come down and touch and go back up, or are we going to go and touch and come back down? They're both going to be down here, or we're going to cross like this red one does. Over here, is this pretty much going to get a curve like this, either up here or down here. Is it up here or is it down here? Right? And it's not going to cross. It's not going to go from up here to down here, because otherwise we would have found an x-intercept somewhere in here, but we didn't. So we got to figure out what's going on. So the vertical asymptotes and the x-intercepts are really what's creating our curiosity. What's happening at all these places? So when we plot points, I said there was going to be a strategy to plotting points. We'll plot points between any combination of x-intercepts and vertical asymptotes. Okay, so we'll plot between this x-intercept and this vertical asymptote, and between this x-intercept and this vertical asymptote, and on the outsides. By outsides, I mean find the thing that's furthest to the left, whether it be a vertical asymptote or an x-intercept, and plot to the left of that. Find the thing that's furthest to the right, whether it be a vertical asymptote or an x-intercept, and plot to the right of that. Okay. So we are going to plot between these two, and between these two, and on the outside, on the right side, and on the left side. So we got 1, 2, 3, 4 places to plot points. Okay. So let's figure out an x that's on the left of this vertical asymptote, and one that's fairly easy. So we have, how about -2? Okay, and over here, somewhere between this x-intercept and this vertical asymptote, so it looks like -1/2. And then somewhere between this and the positive vertical asymptote looks like positive 1/2. And somewhere to the right, on the right side, that looks like 2 would be the simplest. Okay, so let's do that. Let's bring up our calculator. Clear that out. Here's a cool thing about calculators. Let's just create this expression. 2x divided by, here let's use parentheses just to be careful. 2x, that's the numerator, divided by x squared minus 1. Okay, if I press enter, keep in mind somewhere in this calculator is an x value. It thinks it just has x saved as a value somewhere in the calculator. It probably is saying x is 10. That'd be my guess, but I'm not sure. No, it's got to be something else. But anyway, now we're going to use this over again. We just need to tell it what x is going to be. So x is going to be -2. So we do -2, and we hit this STO. That means store as x. Okay, no big deal. X is now -2. But now when we bring up, let's do it again. When we bring up this guy here, now when we say this, we're saying x is -2, and so it's going to tell us -1.33. Okay, that's a little bit of work, but we gain some time back when we just say now, we're going to say -0.5 is x. And then we bring up our expression that we had before and say enter. That's +1.33. Repeating. Okay, and then we'll say 0.5, +0.5 is now x. Whoops, I needed to press store as x. Second entry. I need to bring up this guy again. So now we just said 0.5 is x, and now it's going to put 0.5 in for x. Sorry, I just moved that. -1.33. And now we will let 2 be x. Hit enter. And make sure you go all the way back to this expression, hit enter, and +1.33 repeating. And now we have everything put in there. All right, so let's plot these points. -2, -1.33. So -1.33 would be like right in here. So I'm going to use this color here. Right about there, -1 1/3. Then at -1/2, we're at +1 1/3. We're back down to -1 1/3. And +1 1/3. Okay, so let's start in the middle here. We have a point above and below this x-intercept, so we know that the graph has to cross through to get through all those points, and this one will go all the way up to +∞. This one will go down to -∞, right? It can't come back up and go this way because we would have an x-intercept there. That's how we know it just keeps on going like this. This guy here, we know it's just going to come and approach this horizontal asymptote. It's not going to cross it because we would have found an x-intercept otherwise. And then we can't cross the vertical asymptote, so it must just keep on going like this. Same reasoning leads us to say that we must have a shape like this over on the left side. Okay, so I know that took a while, but we went over everything. We talked about the vertical asymptotes, the horizontal asymptote, x-intercepts, and where to plot points. So we're just going to go through that quickly, more quickly on the next problem here. Just going to keep track of our steps that we're going to follow. Let's do number 16. Y equals 8 over x squared minus x minus 6. All right, let's find vertical asymptotes. First, we'll set the denominator equal to 0, because wherever the denominator is equal to 0, that's where we're going to find vertical asymptotes, saying these x values are bad, because that makes us try and divide by 0. So we're going to solve this equation. Let's try factoring. Multiplies to negative 6 and adds to negative 1. How about 2 and negative 3? So x plus 2 equals 0, x minus 3 equals 0, so x equals negative 2, or x equals 3. Those are the two values of x that would make the denominator 0, and therefore that's where we find our vertical asymptotes. Number 2, we're going to find the x-intercepts. That means we're going to set the numerator equal to 0. This is impossible. There's no x to solve for, and this is false, so no x-intercepts. Okay, so we did that, we did that. Let's find the horizontal asymptote. Okay, now let's just think about what's the biggest power of x in the denominator and the numerator. Well, we got x squared here, so if we put in 100, we're going to get 10,000 when we square it. If we put in 1,000,000, we're going to get 1,000,000,000,000 when we square it. And up here, we just have 8. So we're just going to take 8 and be dividing it by these huge numbers. And so on the ends, the end behavior will be, this graph is just going to get close to 0, because 8 is just going to get divided by this huge number here. So that's your horizontal asymptote. So let's graph all these things. Vertical asymptotes at negative 2. So, and 3. So I'll just put markers there. And I'll bring out the red. Negative 2 and 3. Let's look at our x-intercepts. There aren't any, so we're never going to cross or touch the x-axis. That's good to know. And we have a horizontal asymptote here at y equals 0, or on the x-axis. And then we're going to plot some points. We're going to plot some points, well, here somewhere, because it might come down like this. It's not going to touch the x-axis or cross it. So it either goes like this, you know, making sure that it doesn't cross the vertical asymptotes, or it might do that down here. Then we might have a guy that swoops down like this, or maybe it's down here. We just need to know those things. So we're going to plot a point in here, in here, and in here, in between these vertical asymptotes and on the outsides. So let's set up our table of values here. X will be, let's say, negative 3. And how about 0? 0 is a nice one to put in there. And positive 4. Okay. Let's put a 0 in there. 8. That's all that's going to be the numerator. 8 divided by, this is 0, this is 0, so all that's left is negative 6. So 8 over negative 6, so negative 4/3. Right, so 0, negative 4/3, so that's going to be a little bit bigger than negative 1, a little bit past negative 1. So we see we must have a shape something like this in the, in between these vertical asymptotes. Let's find out what's happening on the left side and the right side. We're going to put a negative 3 in there. Let's just do that in our heads kind of quickly here. We get 9 plus 3, so 12 minus 6, that's 6. 8 divided by 6 is positive 4/3. So negative 3, we get a positive 4/3 right there. And we'll put a 4 in there. Let's see, we get 16 minus 4. That's going to be 12 minus 6. Again, we're going to get 4/3. So that shows us that we must come through this point and approach the horizontal asymptote, never crossing it because we didn't find any x-intercepts, and then not crossing the vertical asymptote because we know that that would make the denominator 0, and that's no good. There we go. We have our graph drawn. All right. Now we'll go on to number, let's see, 17. Yes, 17 is a good one. Okay, so, yes, we want this. And remember our steps here. Alright, so we're going to do number 1, vertical asymptotes. Set the denominator equal to 0. So, elementary at this point. -1, x squared equals -1/2. X equals plus or minus the square root of -1/2. We've got the square root of a negative. That means we have imaginary answers, so no vertical asymptotes. Right? Because these are imaginary, and we don't care about imaginary numbers when we're graphing. Right, how about, let's do part 3, where we find x-intercepts. That's where x squared minus 9 is equal to 0. So x squared equals 9. X equals plus or minus 3. So that's where we find our x-intercepts at plus or minus 3. All right, step 2. Okay, or horizontal asymptote, slightly different now. The denominator is not so much bigger than the numerator. Remember, when we put in 1,000,000 for x and we squared it and then we subtract 9, that's 1,000,000,000 minus 9. That is really, subtracting 9 does not make that much of a difference. Adding 1 is not going to make that much of a difference. So in these problems, it's the biggest power of x. Even if there were another x here, it wouldn't make that big a difference, right? If there were an x to the first power added on, that just wouldn't make that much difference as we put really big numbers in for x. And remember, we're talking about really big numbers or ends, the end behavior. On the ends means big numbers for x. Positive and negative, big numbers for x. So what's that going to be? When we put in a really big number for x, we're going to square it, and down here we're also going to square it. So let's say they're evenly matched, right? They're just going to kind of cancel each other out, right? For the vertical or the horizontal asymptote, it's like we have x squared over 2x squared, and it's like these guys are going to just cancel each other out. When you put in 1,000,000, when you put in 1,000,000,000, 1,000,000,000,000, they're going to be the same thing. So they're going to cancel each other out. So this is just 1/2. So the bigger the number you put in for x, the closer you're going to get to 1/2. So the horizontal asymptote is going to be at, this is f of x. F of x equals 1/2. Okay. So let's graph all these things. No vertical asymptotes, so we don't have to worry about that. X-intercept at positive and -3. Let's grab this color here. -3, +3. Got x-intercepts there. Got a horizontal asymptote at 1/2. So let's say this is 1, so this will be 1/2. We'll just draw this here. All right. So this graph, what does it do? Does it possibly do this? I'm guessing probably it does something like this. Let's see in a little bit here. Or does it, we know it has to approach this horizontal asymptote. We know that. Maybe it does it this way. It just comes down, touches this guy here, goes back up, touches this one, and then keeps going and approaches the horizontal asymptote. We just need to find out what does it do. And that's where plotting points comes in handy. And remember, we're going to plot in between any combination of x-intercepts or vertical asymptotes. We have no vertical asymptotes, so we're just going to plot between the x-intercepts. So there's only one area between that we're going to plot, somewhere in here. And then somewhere over here and somewhere over here on the right. So set up our table of values. Let's do -4. Let's do 0 and +4. That's on the left, in between, and on the right. Okay, so here we go. -4 up here, that's 16 minus 9, that's going to be 7. Okay, 0, got a 0, 0, we end up with -9. Put a 4 in there. Let's see. Oh, hold on. Let's go back up here. We get 16 minus 9, that's 7, but we didn't do anything in the denominator. We got 4 squared, that's 16 times 2, that's 32, plus 1, that's 33. So we have -7. No, we have 7 over 33. 7/33. Just not very big is really all that matters there. Here we do get -9 when we put in 0. And we put in a +4, same thing's going to happen. We're also going to get 7 over 33. Okay, and so let's plot all these points. -4, 7/33. It's just barely above the x-axis. Here we go down to -9, 3, 4, 5, 6, 7, 8, 9, 0, -9, and 4, really small number. Right. So this must go like this, approaching the horizontal asymptote, going through this point, going through the x-intercept, really getting steep now, going down to -9. Back up through the x-axis, and shooting off like that. Okay. Whoa. Kind of crazy. Alright. Yeah, so that's it. We plotted our points. We made sure it goes through all the places that it should. It does approach the horizontal asymptote as it should, and that's what it looks like. Number 22. Y equals x squared minus 5x minus 36 over 3x. And remember the steps we're going to use. Just stick them up there. Do step 1, vertical asymptotes. That's where the denominator is equal to 0 and x equals 0. So that's where our vertical asymptotes are. There's just one of them. We'll do the third step, x-intercepts. That's where the numerator is equal to 0. We'll factor this. X and x. They need to multiply to make -36. They're positive and negative. And add to make -5. So how about -9 and +4? So x equals -4 and x equals 9. These are x-intercepts. That's step 2, horizontal asymptote. There'll only be one, if any. Horizontal asymptote is about the end behavior. Let me just remind you what I mean by that. Let's begin to draw a graph here. I'm going to redraw this. That's better. So let's throw the stuff that we know here. We have vertical asymptote at 0, so let's use a nice bright color so we can see it. We have x-intercepts at -4 and +9. So we have 1, 2, 3, 4. So there's that one. There's another x-intercept. So what we're looking at now is step 2, horizontal asymptote or end behavior. That's on the ends. So just as a reminder, remember we're looking at what happens on the right side, the right end, and the left end. That would be when x starts to get really big. Right? We're not talking about the stuff in the middle. Stuff in the middle is very different. But on the ends, we're just talking about what happens when x gets really, really large, either negative or positive. And say we put in a million in for x and for all these x's. Well, a million squared is a trillion. And then we'd be subtracting 5 million. Subtracting 5 million from a trillion, even though 5 million is big, it's nothing compared to a trillion. If I owed you $1 trillion and I gave you 5 million, you really, if you could grasp how large a trillion was, you wouldn't really care that I gave you 5 million. That's not even putting a dent in a trillion. So that is to say that this 5x, subtracting 5x, just becomes less and less significant as x gets really large. Same with 36. Absolutely, taking away 36 from a trillion is not going to be that big a difference. Okay, so in all of these, it's the thing with the largest exponent that's going to be really the only thing that matters in the end. When x gets to be very large, it's only this number with the largest exponent in the numerator and the largest exponent in the denominator that are going to matter. So it's going to be like we have x squared over 3x. And what's going to happen, this is going to go to, well, this is going to get very large, and this is going to be not even close to as large as this. So it's just going to go off into infinity, right? So that's something to keep in mind. It's just going to go off forever. So it doesn't have a horizontal asymptote that it approaches. It just goes off forever. Now that's assuming that we put in a positive big number for x. What if we put in a negative big number for x? Well, we put a negative in here and it gets squared and it becomes positive. But here we put in a negative and we multiply it by 3, so we just have a negative 3, whatever, 3 times bigger than x. So a positive over a negative, so as x goes to positive infinity, y goes to also positive infinity. As x goes to negative infinity, as you put large negative numbers in for x, y goes also to negative infinity. So over here we're going to see it go off towards positive infinity, and here we're going to see it go off towards negative infinity. Okay, so we're just going to keep that in mind. So we don't have an asymptote, a horizontal asymptote, or otherwise to follow. We technically could find what's called a slant asymptote, but we're not going to do that. So let's plot some points and see what we see. Just remembering that this needs to happen on the ends. Alright, so plotting some points. We're going to plot points, remember, between any combination of vertical asymptotes and x-intercepts. So we have a x-intercept here and a vertical asymptote, so we're going to plot a point somewhere in here. Also somewhere in here, because it's between the vertical asymptote and the x-intercept here. And then on the ends, somewhere on this end and somewhere on this end. Okay, so let's pick some y's, or some x's, and then find the y's. How about negative 5, so that's on the left side. How about negative 1, and positive 1, and positive 10. Okay, so let's see, we put in a negative 5 here, we get 25, minus 25, minus 36, over 3 times 5. This is a little silly. Okay, so I just went ahead and calculated all these. You just need to plug them into the function and find what you get for y. So at negative 5 we get negative 14/15, which is just shy of negative 1. So here's what we know. We know that this needs to go off to negative infinity by our step 2 here. So it goes off to negative infinity, then it needs to come up. Maybe it's going to touch this x-intercept, or maybe it's going to go through it. That's what we're finding out right now. So we'll go on to our next point. Negative 1, comma 10. 4, 5, 6, 7, 8, 9, 10. There we go. Next is 1 and negative 40/3. So let's see. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's just say way down here. Alright, so let's say we know this shape is going to go off to negative infinity. And it's going to go through this point and then through this point. Something like that. And then on this side, we know it's going to come from way down here. And let's see what our other point tells us. Point number, not point number 10, but the point over here at 10. 10 and 7/15, so half-ish. And so this will come out of here, maybe something like this, and then go off to positive infinity as we discovered here. Okay, so something like that. It might actually look completely different, but that definitely is a fairly good picture of what that graph looks like. Alright, well, thanks for watching. I hope that was helpful.